Modern cybersecurity failures often begin long before attackers arrive. They originate quietly during the design and coding of systems. The decisions made by developers, architects, and project managers determine whether software launches with built-in resilience or with hidden weaknesses waiting to be exploited. ISO/IEC 27001 addresses this critical stage through Annexes A.8.25 and A.8.26, which establish controls for the Secure Development Lifecycle, SDLC, and application security requirements. Together, these controls embed security directly into how software is conceived, built, and maintained. They remind organizations that secure applications are not achieved through last-minute testing or after-the-fact patching, but through deliberate discipline from the very first line of code. When these controls are implemented well, vulnerabilities are prevented at their source, reducing the cost, complexity, and disruption of fixing them later in production. Annex A.8.25 sets the expectation that security must be integrated into every stage of the software development lifecycle, from planning and architecture to coding, testing, release, and ongoing maintenance. It applies equally to in-house teams, outsourced vendors, and hybrid development environments that combine internal oversight with external delivery. The goal is to ensure that every project, regardless of scale or ownership, follows a consistent and repeatable approach that treats security as a built-in quality attribute rather than an optional add-on. This control demands governance structures that align development practices with the organization's broader risk management framework, ensuring that developers understand not just how to build, but why certain protections matter in the context of business objectives and compliance obligations. Security begins in the design stage, where architectural and functional decisions have the greatest long-term impact. Threat modeling should be conducted for critical applications to identify likely attack vectors, misuse scenarios, and areas requiring extra protection. Secure architecture principles, such as least privilege, defense in depth, and fail-safe defaults, must guide system design. Security requirements should be documented alongside functional ones so that developers treat them as part of the product's core capabilities, not as secondary tasks. Risk assessment outcomes must feed into design choices, prioritizing mitigations based on potential impact and likelihood. By embedding these considerations early, organizations build applications that are resilient by design, reducing the likelihood of vulnerabilities emerging during later stages. During the coding phase, consistency and adherence to standards are essential. Developers should follow secure coding guidelines tailored to the programming languages and frameworks they use. For example, OWASP recommendations for web applications or SEI cert standards for compiled languages. Peer review of commits and pull requests ensures that multiple sets of eyes validate both functionality and security before code is merged. Automated scanning tools, such as static application security testing, SAST, identify common flaws like injection vulnerabilities or hard-coded credentials before they reach production. Version control systems must be tightly managed, granting write permissions only to authorized contributors and maintaining immutable histories for accountability. These practices not only prevent insecure code, but also create an auditable record of how quality and security have been enforced throughout development. Testing and validation extend the SDLC's defensive perimeter. Static analysis examines code structure for vulnerabilities without execution, while dynamic testing simulates attacks against running applications to observe behavior. Penetration testing should occur before production release, particularly for high-risk or customer-facing systems, providing a realistic measure of resilience. Fuzzing and exploratory testing introduce random or malformed inputs to uncover edge case weaknesses that scripted tests might miss. Every discovered issue must be documented, tracked, and remediated, with verification confirming that fixes are effective and have not introduced regressions. These layers of testing ensure that by the time an application reaches production, its security posture is known, quantified, and defensible. Discipline continues beyond deployment through release management and ongoing maintenance. Each release should pass through a formal approval gate, verifying that all required tests have been completed and security criteria met. Rollback or kill switch mechanisms must exist in case a new version introduces unexpected instability or vulnerability. Post-release, vulnerability monitoring continues through automated scanning, user feedback, and vendor advisories. Patch cycles integrate with operational processes to ensure timely updates across all deployed environments. This ongoing vigilance closes the loop of the secure development lifecycle, reinforcing the idea that security is not a one-time event, but a continual practice.
Auditors assessing compliance with A.8.25 look for tangible evidence that security is systematically woven into the SDLC. Policies and standards documents must define roles, responsibilities, and expectations for secure design and coding. Records from design reviews, threat models, and approval meetings demonstrate that security assessments occurred before development began. Test reports from vulnerability scans, penetration tests, and remediation tracking provide proof that issues are discovered and resolved. Version histories showing peer review and approval logs illustrate process maturity. Collectively, these artifacts reveal not only what was built, but how responsibly it was built, transforming security from an aspiration into a traceable methodology.
The consequences of neglecting a secure SDLC can be severe. Input validation errors, one of the oldest and most preventable flaws, continue to enable injection attacks because they were overlooked during design. Deadline pressure may lead to the release of critical vulnerabilities without mitigation, resulting in breaches and emergency patching later. Custom applications deployed without a patch management plan remain vulnerable for years, creating persistent risk. Outsourced development without proper oversight can introduce unvetted libraries, insecure integrations, or even malicious code. Each of these examples underscores ISO's rationale for A.8.25, preventing security debt before it compounds into operational or reputational loss. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Application security requirements begin with understanding what the software will protect and why. Each application should have its own risk and data classification profile, defining the sensitivity of the information it handles and the potential impact of compromise. From this foundation, requirements are derived to govern authentication, authorization, encryption, input validation, error handling, logging, and monitoring. For example, an internal scheduling tool may only need corporate single sign-on and basic logging, while a public-facing financial portal requires multi-factor authentication, encrypted sessions, transaction signing, and audit trails. The principle is proportionality, security aligned to the sensitivity of the data and the exposure of the system. Requirements fall into several broad categories that serve as a blueprint for secure behavior. Authentication and session management ensure that users and systems prove identity reliably, often through MFA, tokenization, or federated identity protocols. Authorization and role enforcement define what authenticated entities are allowed to do, enforcing least privilege and separation of duties. Cryptographic controls specify when and how data must be encrypted, whether in transit using TLS or at rest using AES or other approved standards. Logging and monitoring requirements define what activities must be recorded for traceability, forming the foundation for auditing and incident response. Together, these categories transform abstract policies into concrete specifications that developers can implement and testers can verify. To operationalize these requirements, organizations create structured mechanisms that integrate security from project initiation. Templates for project charters or design documents include mandatory sections for security requirements, ensuring they are not overlooked during scoping. Standardized checklists guide developers and architects through control expectations for different application types, web, mobile, API, or embedded systems. Mapping requirements to external regulatory frameworks such as PCI DSS, HIPAA, or GDPR ensures legal and compliance obligations are automatically reflected in system design. When procuring third-party or outsourced solutions, security clauses embedded in RFPs and contracts hold suppliers to the same standards as internal teams. This consistency ensures that every piece of software, whether built or bought, contributes to the organization's overall security posture. Auditors examining compliance with A.8.26 expect clear documentation demonstrating that requirements were defined, implemented, and verified. Application design documents should list specific security requirements and show how they align to identified risks. A traceability matrix should link each requirement to corresponding test results or verification activities, demonstrating end-to-end accountability. Contracts with developers or vendors must include clauses specifying adherence to organizational security policies and frameworks. Change records should show updates to requirements in response to emerging threats, such as new OWASP Top 10 categories or shifts in compliance obligations. Collectively, this evidence shows that security expectations are not static, they evolve alongside the applications they protect. The absence of clear security requirements can have far-reaching effects. When critical controls are overlooked during design, vulnerabilities often surface late in testing, or worse, after deployment, requiring expensive rework and downtime. Inconsistent application of security across different systems leads to uneven protection, where one business unit might implement MFA, while another still relies on passwords alone. Failure to define encryption standards or privacy safeguards can result in regulatory breaches under frameworks like GDPR, attracting fines and reputational harm. Retroactively adding missing protections inflates project costs and delays releases, proving that proactive requirement setting is far cheaper than reactive remediation. Across industries, organizations apply this control in ways that directly support their business missions. Banking and fintech applications require multi-factor authentication and transaction verification built directly into their design, ensuring that identity assurance is intrinsic rather than bolted on. Healthcare systems embed detailed audit logging and access traceability into electronic health record platforms, satisfying HIPAA requirements for accountability. E-commerce platforms integrate PCI DSS standards into checkout flows from the outset, encrypting payment data and tokenizing customer credentials. Government applications align accessibility with security, enforcing role-based access while meeting digital inclusion standards. These examples demonstrate that defining requirements early allows organizations to innovate securely rather than constrain creativity later. Together, Annexes 8.8.25 and 8.26 form the blueprint for secure software creation. The SDLC provides the structured process, how teams plan, build, test, and maintain securely, while application security requirements define the content, setting the bar for what secure actually means. A lifecycle without explicit requirements risks producing functional but unsafe software. Requirements without lifecycle discipline remain theoretical checklists never enforced in practice. When combined, they produce applications that are secure, auditable, and maintainable. They create a continuous improvement cycle where every project contributes lessons back into governance, refining standards for the next generation of software. By embedding these two controls into development culture, organizations evolve from reactive security to proactive assurance engineering. Security becomes a measurable outcome of process maturity rather than an emergency response to incidents. Developers gain clarity, auditors gain transparency, and business leaders gain confidence that new applications will enhance capability without increasing exposure. Annexes A.8.25 and A.8.26 thus embody one of ISO/ISO 27001's most forward-looking ideas. That resilience begins not with firewalls or scanners, but with disciplined design thinking. When development and security move in tandem, the result is not just secure code, but sustainable trust in the systems that run the modern enterprise.